Welcome, friends. I'm so glad you're here, whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion. You found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the deepest questions of physics, where gravity itself might be nothing more than an elegant illusion. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The apple falls. It has always fallen, will always fall, tracing the same inevitable arc from branch to earth that inspired Newton's mind 3 centuries ago. Red skin catches afternoon light as it tumbles through air thick with the scent of late summer orchards. The fruit drops 20 feet in less than 2 seconds, striking soil with the softest impact, a sound so gentle it barely disturbs the silence of Woolsthorpe Manor's gardens. But in 1907, a young patent clerk in Bern sits at his wooden desk and imagines something entirely different. Albert Einstein, 28 years old and still unknown to the scientific world, pictures a man trapped inside a windowless elevator. The thought arrives unbidden on a Tuesday morning, interrupting his review of electromagnetic patents. In that simple mental image, gravity begins its slow dissolution. The elevator falls freely through empty space, plummeting toward Earth with perfect acceleration. Inside, cut off from any external reference point, the man experiences something extraordinary. He floats weightless, his feet lifted gently from the floor, his arms drifting outward without effort. His fountain pen hovers beside his cheek, neither rising nor falling. Coffee spills from his morning cup and hangs in perfect spheres, each droplet suspended like liquid stars in the chamber's still air. To this trapped observer, gravity has vanished completely, not weakened, not diminished, simply gone. He pushes against the elevator's walls and finds himself floating freely in what seems like zero gravity, experiencing the same weightlessness that astronauts would later describe in orbit. His watch ticks normally, his breathing continues unchanged, yet the fundamental force that has governed his entire existence appears to have switched itself off. Einstein follows the thought experiment further. Switch perspectives now. Step outside the falling elevator and observe from a distant vantage point. From here, gravity reveals its traditional face. The entire chamber plunges earthward with relentless acceleration, pulled by the same force that draws all objects toward massive bodies. The man inside, the floating pen, the suspended coffee, all of them fall together in Earth's gravitational embrace. The same phenomenon wears 2 completely different faces. One observer, trapped within the system, sees the complete absence of gravity. Another observer, watching from outside, sees gravity's pure and total expression. Both perspectives are equally valid. Both are absolutely correct. Einstein realizes they must both be describing the same underlying reality. This is the equivalence principle, whispered into existence in that moment of insight. Local acceleration and gravitational force become mathematically and physically indistinguishable. Not through clever tricks of mathematics, not through philosophical sleight of hand, but through the fundamental architecture of reality itself. The universe operates according to principles so elegant that seemingly opposite experiences can be identical at their core. The implications ripple outward like waves through still water, If acceleration and gravity are truly equivalent, then gravity cannot be a force in the traditional sense. Forces act upon objects, pulling and pushing them through space. But gravity appears to act on the stage itself, on the very fabric of space and time through which objects move. The apple falls not because Earth reaches out with invisible hands to pull it downward, but because Earth's mass warps the geometry of space-time itself. In this new vision, the apple simply follows the straightest possible path through curved space-time. What appears to be a downward arc through three-dimensional space is actually a straight line, a geodesic, through the four-dimensional continuum of space and time. The apple moves naturally, without external forces, tracing the path that geometry demands. It is the most effortless motion in the universe, yet to observers embedded in the same curved space-time, it appears as accelerated fall. Einstein works through the mathematics slowly, carefully, over the following years. Each equation confirms what his intuition first glimpsed in that imaginary elevator. Massive objects do not attract smaller ones through mysterious action at a distance. They simply exist, and their existence bends the fabric of reality around them. Picture a bowling ball placed on a stretched rubber sheet. The heavy sphere creates a depression, and smaller marbles rolled nearby naturally curve toward it, following the contours that the bowling ball's presence has created. But this analogy, helpful as it is, barely captures the profound strangeness of the actual mechanism. The rubber sheet is not a thing that exists in space. It is space itself, combined with time into a single four-dimensional manifold. The bowling ball does not sit on this surface. It is embedded within it, warping not just the spatial dimensions but temporal ones as well. Time itself runs slower in regions of stronger gravitational field, creating a gradient that contributes to what we experience as gravitational attraction. In the quiet of that Swiss patent office, surrounded by applications for electromagnetic devices and mechanical innovations, Einstein glimpses what gravity might truly be. Not a force pulling objects together, but the natural consequence of mass energy curving the very stage upon which cosmic drama unfolds. Matter tells space-time how to curve, and curved space-time tells matter how to move. It is a feedback loop of perfect elegance, a cosmic dance between substance and geometry that creates the illusion of invisible forces reaching across vast distances. How deeply strange that the most familiar sensation, weight pressing through our feet, the tug we feel when we lift heavy objects, the inevitable pull that draws dropped items toward the floor, might be the universe's most sophisticated illusion. We feel pinned to Earth's surface not by gravitational chains, but because we resist the natural motion that space-time geometry demands of us. We are not being pulled downward. We are being held up by the electromagnetic forces in our bodies, fighting against the geodesic paths that curved reality offers as the most natural routes through existence. The apple, in its brief journey from branch to earth, experiences no forces at all. It follows the straightest line available through space-time curved by Earth's presence, only from our perspective, anchored to the planet's surface by forces that resist space-time's natural flow. Does the apple appear to accelerate downward under gravity's influence? In its own reference frame, the apple moves inertially, freely, without any sensation of falling until the electromagnetic forces in the soil bring its journey to an abrupt end. Einstein's revelation changes everything while changing nothing at all. Apples continue falling in orchards around the world. Planets maintain their ancient orbits around stars. Ocean tides rise and fall in their eternal rhythm. But underneath these familiar phenomena lies a more elegant and mysterious truth. That gravity, the force that seems to govern every motion in the cosmos might be nothing more than the universe expressing its most fundamental geometric nature. The question echoes through the decades that follow. If gravity is geometry rather than force, what does this mean for our understanding of reality itself? The apple falls upward through space-time, following invisible contours that bend around Earth's mass, while we stand on the surface feeling the weight of existence itself, mistaking the natural flow of curved reality for something that pulls us down. The fabric stretches, not cloth or canvas, but something far more fundamental, the very substrate upon which existence unfolds. Space-time spreads across dimensions that human minds can barely grasp, invisible and intangible, yet more real than any material substance. This cosmic fabric responds to the presence of mass and energy like a membrane under tension, warping and curving in ways that create the phenomena we mistake for gravitational force. Picture the demonstration that appears in physics classrooms around the world. A large rubber sheet stretched tight across a circular frame, its surface smooth and flat in the absence of any disturbance. Roll a marble across this pristine geometry and it travels in perfect straight lines, maintaining constant velocity until friction gradually brings it to rest. The sheet remains undisturbed, offering no resistance to the marble's motion, no deflection from its chosen path. Now place a bowling ball at the center of the stretched membrane. The heavy sphere immediately creates a depression, bending the sheet's surface into a smooth, curved well that extends outward in all directions. The once flat geometry becomes a landscape of hills and valleys, with the deepest point directly beneath the bowling ball's weight. The curvature follows precise mathematical relationships, steeper near the central mass, gradually flattening toward the edges where the sheet returns to its original flatness. Roll the marble again. This time it cannot maintain its straight-line path. The curved geometry guides its motion, deflecting it toward the depression created by the bowling ball. If the marble approaches with sufficient speed, it might circle the depression in stable orbit, trapped neither by mysterious forces nor invisible strings, but by the shape of the surface itself. The curvature provides the only available paths, and the marble simply follows whichever route its initial conditions determine. This analogy, imperfect though it remains, offers a glimpse into Einstein's profound insight. Massive objects like stars and planets do not reach across empty space to pull on distant bodies. Instead, they warp the very geometry through which other objects must travel. The warping extends infinitely outward, growing weaker with distance but never quite disappearing entirely. Every particle of matter contributes to space-time's overall curvature, creating a cosmic landscape of invisible hills and valleys that guide the motion of everything from photons to galaxies. But the rubber sheet comparison fails to capture the full strangeness of the actual phenomenon. Real space-time possesses 4 dimensions rather than 2, 3 of space and 1 of time, all woven together into a single mathematical structure that Einstein called the space-time continuum. The curvature affects not just spatial paths but temporal ones as well. Clocks run slower in regions of stronger gravitational field, where space-time curves more sharply around concentrated mass. This temporal warping proves just as important as spatial distortion in creating what we experience as gravitational effects. Objects fall toward massive bodies partly because space curves inward, but also because time dilates differently at various distances from the center of mass. The complex interplay between spatial and temporal curvature creates geodesics, the straightest possible paths through curved spacetime, that appear as accelerated motion to observers embedded within the same curved geometry. Consider Earth's effect on the spacetime surrounding it. Our planet's mass creates a depression in the four-dimensional continuum, with the curvature strongest at the surface and gradually weakening with altitude. Astronauts in the International Space Station orbit within this curved spacetime, following geodesic paths that require no propulsion to maintain. They experience weightlessness not because gravity has vanished, but because they move freely through spacetime's natural geometry, without any forces acting to deflect them from their geodesic trajectories. The station and its crew fall continuously toward Earth, but their horizontal velocity carries them forward at precisely the right speed to match the planet's curvature. They trace a closed geodesic loop through spacetime, circling endlessly in a path that represents pure inertial motion through curved geometry. No engines fire to maintain the orbit. No mysterious forces balance against gravitational attraction. The spacecraft simply follows the straightest available route through warped spacetime, and that route happens to form a stable ellipse around Earth's mass. Meanwhile, those of us standing on the planet's surface experience weight and gravitational pull because we resist the natural geodesic paths that spacetime offers. The electromagnetic forces between atoms in our bodies and in the ground beneath our feet prevent us from following the curved geometry that would carry us toward Earth's center. We feel pressed against the surface not because gravity pulls us down, but because the surface pushes up against our natural tendency to follow spacetime's curvature inward. This reversal of perspective transforms our understanding of fundamental experiences. When you jump from a diving board, you do not fall under gravity's influence. You finally achieve free motion through spacetime, following a geodesic path until the electromagnetic forces in water or ground interrupt your journey. The sensation of falling is actually the sensation of moving naturally through curved geometry, unimpeded by other forces. Only when something stops your geodesic motion do you feel the jarring return to artificial force-dominated movement. The mathematics that describe these curved geodesics grew from Einstein's collaboration with mathematician Marcel Grossmann, who introduced him to the tensor calculus needed to work with curved space-time geometries. The resulting field equations, published in 1915 as the General Theory of Relativity, reveal how mass-energy density determines space-time curvature, and how that curvature in turn guides the motion of all objects and energy through the cosmic landscape. These equations predict phenomena that Newton's gravitational theory cannot explain. Light beams bend when passing near massive objects, following curved geodesics through warped space-time. Time dilation affects clocks in gravitational fields, with precise effects that satellite navigation systems must correct for millions of times each day. Mercury's orbit precesses slightly faster than Newtonian mechanics predicts, tracing a slowly rotating ellipse as it follows geodesic paths through the Sun's curved spacetime. Yet questions remain at the boundaries of understanding. Quantum mechanics describes matter and energy in terms of discrete particles and probability waves, while general relativity treats spacetime as a smooth, continuous manifold. The two theories resist unification, offering contradictory descriptions of reality at the smallest scales where quantum effects meet gravitational ones. Perhaps spacetime itself emerges from more fundamental quantum processes, making the curved fabric of reality another layer of illusion built upon deeper mysteries. The bowling ball rests in its depression, warping the rubber sheet in patterns that guide marble trajectories around its circumference. But the bowling ball itself consists of atoms held together by electromagnetic forces, atoms built from quarks and electrons governed by quantum field equations that have no clear relationship to space-time geometry. The fabric stretches under influences that may not be fundamental forces at all, but emergent phenomena arising from the quantum foam that underlies all existence. Still, the geodesics continue their ancient patterns. Planets orbit stars along paths carved by space-time curvature. Light travels through the universe following routes bent by every massive object it encounters. And somewhere in the curved geometry around Earth, the International Space Station traces its endless ellipse, its crew floating weightless through a reality where gravity reveals itself as nothing more than the shape of existence itself. Dressed in the familiar costume of force and attraction that consciousness mistakes for fundamental truth. The eclipse begins at dawn. On May 29, 1919, the moon's shadow creeps across the Atlantic Ocean, racing eastward at 1,700 miles per hour toward the coast of West Africa, in the small town of Principe, off the shores of Equatorial Guinea. British astronomer Arthur Eddington adjusts his camera equipment one final time. The photographic plates lie ready in their holders, waiting to capture starlight that should not exist. According to Newton's theory, light possesses no mass. Massless things should not respond to gravitational attraction. The stars visible near the sun's edge during totality should appear in their normal positions, unaffected by the solar gravitational field. But Einstein's new theory suggests something different, that light follows geodesics through curved space-time, bending around massive objects whether it carries mass or not. The moon slides across the solar disk with geological patience. Totality will last only 6 minutes and 51 seconds in Principe's location. Barely enough time to photograph the star field surrounding the eclipsed sun. Eddington has practiced the procedure dozens of times, rehearsing each movement until his hands can work independently of conscious thought. The stakes could not be higher. These photographs might confirm or destroy Einstein's radical reimagining of gravity itself, as the last sliver of solar brightness disappears behind the lunar disk. Stars suddenly blaze into visibility around the darkened sun. The corona streams outward in ethereal ribbons of light, but Eddington ignores this celestial beauty. His cameras click methodically, capturing precise positions of stars that appear near the sun's limb. If Einstein is correct, these stellar positions should be shifted slightly outward from their normal locations, displaced by the sun's gravitational influence on the light itself. The shift Einstein predicts measures impossibly small, just 1.75 arcseconds for stars appearing at the very edge of the solar disk. This represents an angular displacement so tiny that it would take more than 1 million such deflections to equal the apparent width of the full moon. Detecting such minute changes requires photographic precision at the absolute limits of 1919 technology, compounded by the challenges of working during the brief, twilight-like conditions of totality. 6 minutes pass like heartbeats. The moon continues its journey across the solar face, and the first brilliant point of returning sunlight signals the end of totality. The stars vanish instantly, overwhelmed by the sun's restored brightness. Eddington's photographs are complete, but months of careful analysis lie ahead before their secret can be revealed. Meanwhile, half a world away, a second expedition led by Andrew Crommelin observes the same eclipse from Sobral, Brazil. Their photographic equipment supplements Eddington's work, providing independent measurements of the same stellar positions during totality. The redundancy is crucial. Such an extraordinary claim requires extraordinary evidence, gathered by multiple observers using different instruments under varying conditions. The analysis begins immediately upon the expedition's return to England. Each photographic plate must be measured with micrometer precision, comparing star positions during the eclipse with reference photographs taken months earlier when the same stars appeared in nighttime sky. Far from the sun's influence, the tedious work proceeds measurement by measurement, star by star, as the accumulated data slowly reveals whether Einstein's prediction matches observational reality. The results emerge gradually through the autumn of 1919. Eddington's measurements from Principe show stellar displacements averaging 1.61 arcseconds, remarkably close to Einstein's predicted value of 1.75 arcseconds. Cromlin's Brazilian observations prove less definitive due to equipment problems during totality, but they generally support the same conclusion. Light bends around massive objects, following curved geodesics through warped spacetime exactly as Einstein's theory demands. The announcement comes on November 6, 1919, at a joint meeting of the Royal Society and Royal Astronomical Society in London. J. Thomson, the elderly physicist who discovered the electron, rises to address the assembly. This result is not an isolated one, he declares to the packed auditorium. It is a whole continent of scientific ideas. Newton's law of universal gravitation, unchallenged for more than 2 centuries, suddenly requires fundamental revision. The philosophical implications ripple outward like earthquake waves. Light, previously understood as pure electromagnetic radiation, reveals itself as subject to gravitational influences despite carrying no mass. This suggests that gravity affects not just matter but the very geometry through which all phenomena must travel. Space and time themselves become dynamic participants in cosmic evolution rather than passive stages upon which events unfold. Yet mysteries multiply alongside confirmations. The precise mechanism by which mass energy creates space-time curvature remains hidden within Einstein's field equations. Mathematical relationships so complex that exact solutions exist for only the simplest configurations. The sun's spherical symmetry permits analytical treatment, but real astronomical objects, rotating stars, binary systems, galaxies with complex mass distributions, require approximations that may miss crucial details. Even more puzzling, the bending of light suggests that photons follow the same geodesics as massive particles, despite fundamental differences in their physical nature. Particles with mass can move at any velocity less than the speed of light, while photons always travel at exactly light speed through vacuum. Yet both trace paths determined by space-time curvature, as if the geometry itself possesses a universal character that transcends the specific properties of whatever moves through it. The eclipse measurements also raise questions about the nature of light itself. If photons respond to gravitational fields, do they also generate such fields? Einstein's mass-energy equivalence suggests that light carries energy, and energy contributes to space-time curvature according to the field equations. This means that light not only follows curved geodesics, but also participates in creating the curvature through which it travels, a feedback loop between electromagnetic radiation and gravitational geometry. Modern measurements confirm Eddington's results with extraordinary precision. Radio telescopes track quasar positions as they pass behind the Sun, detecting gravitational light-bending effects with accuracies approaching 1 part in 10,000. Satellite experiments measure gravitational redshift, the frequency changes that occur when light climbs out of gravitational wells, confirming Einstein's predictions to 15 decimal places. Yet each confirmation deepens the mystery of how geometric curvature emerges from the quantum interactions that govern matter and energy at fundamental levels. The stars continue their apparent dance around the eclipsed sun, their light following invisible highways carved through space-time by the solar gravitational field. In 6 minutes of totality, human understanding shifted from Newtonian certainty to relativistic mystery. Light revealed its hidden sensitivity to gravitational influences, confirming that even massless phenomena must navigate the curved geometry that massive objects create around themselves. But the deeper questions remain suspended like stellar images in the cosmic dark. What is the relationship between the smooth curvature described by Einstein's equations and the discrete, probabilistic reality revealed by quantum mechanics? How does space-time geometry emerge from whatever more fundamental processes underlie physical existence? The bent starlight points toward answers that continue to elude human comprehension, leading deeper into realms where gravity itself may prove to be just another beautiful illusion masking stranger truths. The elevator waits in perfect stillness. No sound penetrates its metal walls. No vibration disturbs the air within its sealed chamber. The man inside floats in the center of the space, his feet several inches above what he assumes to be the floor, his arms extended outward for balance in an environment where balance has lost all meaning. His coffee cup drifts beside his left shoulder, its contents forming perfect spheres that catch and scatter the overhead light in patterns of liquid geometry. This is Einstein's most famous thought experiment, refined and polished through decades of contemplation into a philosophical instrument of surgical precision. The scenario appears deceptively simple, a windowless elevator containing a single observer, isolated from any external reference points that might reveal the nature of his situation. Yet within this imaginary box lies the key to understanding why gravity might be nothing more than a persistent illusion created by the interplay between acceleration, geometry, and conscious observation. The man experiences weightlessness in its purest form. Every object in the elevator, his pen, his wristwatch, loose coins from his pocket, even individual dust motes floating in the still air, maintains perfect relative position. Nothing falls, nothing rises. The sensation matches exactly what astronauts would later describe during orbital flight, a complete absence of gravitational effects, as if some cosmic switch has been thrown to disable the fundamental force that normally governs all motion. But consider the situation from an external perspective. The elevator plummets through space in perfect freefall, accelerating downward at precisely 9.8 meters per second squared under Earth's gravitational influence. Every atom of the chamber and everything within it falls together at identical rates, creating the illusion of weightlessness for the trapped observer. Gravity has not vanished. It has become invisible by affecting everything equally. Einstein's insight cuts deeper than this simple observation. If the falling man cannot distinguish his situation from true zero gravity, then perhaps there is no physical difference between the two scenarios. Local acceleration and gravitational effects become not merely similar but fundamentally identical. This equivalence suggests that gravity itself might be a kind of pseudo-force, an apparent effect created by observing accelerated motion from within an accelerated reference frame. The implications echo through every aspect of physical theory. In Newton's framework, the man in the elevator experiences two distinct forces, gravity pulling him downward and the electromagnetic forces in his body resisting that pull. The balance between these forces creates his sensation of weight when the elevator remains stationary. But during freefall, both the man and his environment accelerate identically under gravitational influence, eliminating any relative motion between his body and the chamber walls. Einstein realizes that this situation reveals something profound about the nature of inertial reference frames. In special relativity, he had established that uniform motion creates no detectable physical effects within a closed system. An observer moving at constant velocity cannot determine his speed without reference to external landmarks. But the equivalence principle extends this concept to include accelerated motion under gravitational influence. The freely falling elevator becomes a locally inertial reference frame, within which the laws of physics take their simplest form. Particles move in straight lines unless acted upon by non-gravitational forces. Light travels in perfectly straight paths. Clocks tick at their natural rates. All the phenomena that special relativity describes for unaccelerated motion appear within the falling chamber, despite its obvious acceleration relative to Earth's surface. This leads to the most startling conclusion of all. Observers who feel the effects of gravity, like those of us standing on Earth's surface, exist in accelerated reference frames. We are not at rest in any meaningful sense. Instead, we are constantly accelerated upward by the electromagnetic forces that prevent us from following our natural geodesic paths through curved spacetime. The sensation of weight comes not from gravity pulling us down, but from forces pushing us up against the natural motion that spacetime geometry would otherwise dictate. The mathematical formalism makes this reversal explicit. In Einstein's field equations, freely falling observers follow geodesics, the straightest possible paths through curved spacetime. These represent true inertial motion, requiring no forces to maintain. Meanwhile, observers who remain at fixed positions relative to massive objects must be accelerated continuously to prevent them from following their natural geodesic trajectories. The surface of Earth accelerates upward at 9.8 meters per second squared, carrying us along despite our tendency to move inertially through the curved space-time that Earth's mass creates. Yet questions multiply at the boundaries of this elegant framework. The equivalence principle works perfectly within small local regions of space-time, but breaks down over larger scales where tidal effects become noticeable. Two objects falling side by side toward Earth will gradually converge as they follow slightly different geodesics toward the planet's center. This tidal acceleration reveals the presence of gravitational gradients that purely local equivalence cannot explain away. The elevator thought experiment also assumes perfect uniformity of gravitational fields, a condition that never exists in the real universe. Every massive object creates unique patterns of space-time curvature, with field strength varying according to complex functions of distance and direction. The moon's gravity tugs differently on different parts of Earth, creating ocean ties that no amount of local acceleration can replicate. These variations in gravitational gradient represent genuine physical effects that transcend any simple equivalence between acceleration and gravity. Even more mysterious is the question of what determines the specific geodesic paths that objects follow through curved space-time. Einstein's equations describe how mass energy creates curvature, and how curvature guides motion, but they remain silent about the deeper mechanisms that connect geometry to physics. Why should particles with different masses follow identical paths through gravitational fields? What aspect of space-time geometry compels both photons and planets to trace the same geodesic routes around massive objects? The quantum mechanical description of particles adds further layers of confusion. At microscopic scales, matter behaves according to probability waves that seem to have no obvious relationship to classical geodesics through curved spacetime. Electrons in atoms occupy orbital states defined by quantum field equations, not paths determined by gravitational geometry. The smooth curvature that guides planetary motion appears disconnected from the discrete, probabilistic reality that governs atomic structure. Modern experiments continue testing the equivalence principle with ever-increasing precision. Satellite missions compare the freefall acceleration of different materials, searching for tiny violations that might reveal the limits of Einstein's insight. So far, all tests confirm that gravitational and inertial mass remain identical to better than 1 part in 10 trillion, supporting the conclusion that locally uniform acceleration and gravitational fields create physically indistinguishable effects. But the perfect equivalence itself raises deeper questions about the fundamental nature of physical law. Why should the universe be constructed so that geometry and acceleration produce identical effects? What deeper principle connects the curvature of space-time to the experience of conscious observers embedded within that curvature? The equivalence principle describes how gravity works, but it cannot explain why space-time possesses this particular geometric character, rather than some other mathematical structure. The man in the elevator continues floating in his sealed chamber, unaware whether he falls through Earth's gravitational field or drifts through empty space, far from any massive objects. His experience remains identical in either case, suggesting that the distinction between these scenarios might be less fundamental than it appears. Perhaps gravity is indeed nothing more than acceleration viewed from within an accelerated reference frame, making it the most persistent and universal illusion that consciousness encounters in its attempts to understand physical reality. Yet as the thought experiment plays out across decades of theoretical development, its implications grow stranger rather than clearer. If gravity is geometric rather than force-like, what does this mean for the other fundamental interactions? Do electromagnetic and nuclear forces also emerge from hidden geometries in higher dimensional spaces? The elevator falls through possibilities as vast as the universe itself, carrying its passenger toward insights that remain suspended between revelation and mystery. The quantum foam seethes, at distances smaller than the Planck length, roughly 10 circumflex 35 meters, a scale so tiny that comparing it to an atom would be like comparing an atom to the solar system. Space-time itself loses all meaning. Here, the smooth geometric fabric that Einstein described dissolves into a probabilistic froth of virtual particles, spontaneous fluctuations, and uncertainty relations that make the very concept of position and momentum simultaneously meaningless. Particles materialize from nothing, borrowing energy from the vacuum itself through the strange accounting principles of Heisenberg's uncertainty principle. Electron-positron pairs flicker into existence for immeasurably brief moments before annihilating back into pure energy. Photons emerge from empty space, travel infinitesimal distances, then vanish without trace. The vacuum writhes with activity invisible to classical observation, filled with phenomena that quantum field theory describes in exquisite mathematical detail. This quantum mechanical reality governs the behavior of matter and energy at the smallest scales with extraordinary precision. The electromagnetic force emerges from the exchange of virtual photons between charged particles. The strong nuclear force binds quarks together through gluon interactions described by quantum chromodynamics. The weak nuclear force governs radioactive decay through processes involving W and Z bosons. Each interaction follows probability rules encoded in quantum field equations that predict experimental results to 15 decimal places, but gravity remains stubbornly aloof from this quantum description. Einstein's field equations treat spacetime as a smooth, continuous manifold, infinitely divisible, perfectly differentiable, exempt from the uncertainty relations that constrain all other physical phenomena. General relativity assumes that spacetime curvature can be measured with arbitrary precision, that geodesic paths represent exact solutions rather than probability distributions, that the geometry itself remains classical even when everything moving through it follows quantum mechanical rules. This separation creates profound conceptual difficulties at the boundaries where quantum effects and gravitational ones should meet, near black hole event horizons, where gravitational fields grow incredibly strong over distances comparable to particle wavelengths. Neither classical geometry nor quantum field theory provides reliable descriptions. In the first moments after the Big Bang, when the entire observable universe compressed into regions smaller than atomic nuclei, quantum gravitational effects must have dominated all other physics, yet no consistent theory exists to describe such conditions. The measurement problem becomes particularly acute when attempting to detect gravitational phenomena at quantum scales. General relativity predicts that accelerating masses should radiate gravitational waves, ripples in spacetime curvature that propagate outward at light speed. But these waves carry energy, and energy at quantum scales comes in discrete packets called quanta. If gravitational waves are quantized, then gravity itself must emerge from the exchange of quantum particles, hypothetical gravitons that have never been directly observed. The search for gravitons encounters immediate difficulties, unlike photons, which mediate electromagnetic forces and can be easily detected and manipulated. Gravitons interact so weakly with matter that individual particles would be virtually impossible to observe. The energy required to detect a single graviton would be comparable to the rest mass energy of large asteroids, far beyond any conceivable experimental capability. Gravity reveals its quantum nature, if at all, only through indirect statistical effects accumulated over enormous numbers of gravitational interactions. Even more puzzling is the question of how gravitational fields should behave when they encounter quantum superposition states. If an electron can exist in multiple positions simultaneously until measured, what happens to the gravitational field that the electron generates? Should spacetime curvature itself exist in superposition, with multiple geometric configurations overlapping until some measurement process forces the system to collapse into a single classical state? Some physicists propose that consciousness itself might play a crucial role in resolving these quantum gravitational paradoxes. Perhaps the act of measurement by conscious observers causes both quantum wave functions and spacetime geometry to collapse from superposition into definite classical states. This suggestion pushes the mystery deeper rather than solving it. Why should consciousness possess special status in determining physical reality? What physical mechanism allows mental states to influence gravitational fields? Alternative approaches attempt to quantize gravity directly by treating spacetime itself as emerging from more fundamental quantum processes. In loop quantum gravity, space and time consist of discrete, indivisible units connected in network-like structures that create the illusion of smooth geometry at large scales. The area of any surface and the volume of any region come in minimum quantum units, making space-time inherently granular rather than continuous. String theory takes a different approach, proposing that all fundamental particles, including hypothetical gravitons, consist of vibrating one-dimensional loops moving through spaces with extra hidden dimensions. In this framework, gravity appears weak compared to other forces because gravitons can escape into the extra dimensions, spreading their effects across a larger arena than the three spatial dimensions we directly experience. The quantum mechanical vibrations of strings in 10 or 11-dimensional space create all observed particles and forces through different oscillation patterns. But both approaches encounter difficulties when tested against experimental observation. Loop quantum gravity makes specific predictions about spacetime structure at the smallest scales, but these effects remain far below current observational capabilities. String theory requires enormous energies to reveal its distinctive signatures, energies comparable to those present during the first moments after the Big Bang. Neither theory has yet produced testable predictions that would distinguish it from classical general relativity under currently accessible conditions. The fundamental problem may lie deeper than current theoretical approaches suggest. Perhaps the attempt to quantize gravity misses the point entirely. If gravity emerges from more basic processes, if space-time geometry itself represents an approximation valid only at scales much larger than the Planck length, Then the search for gravitons and quantum gravitational effects might be pursuing illusions created by applying classical concepts beyond their legitimate domains. This possibility aligns with the broader theme of gravity as illusion rather than fundamental force. If spacetime curvature emerges from quantum entanglement patterns between fundamental degrees of freedom, then gravity becomes an effective theory, accurate within its domain of applicability, but ultimately reducible to more basic quantum mechanical processes. The smooth geometric description that works so well for planets and stars might break down completely when applied to phenomena occurring at energy scales where quantum effects dominate. Yet even this emergent picture raises profound questions about the nature of physical reality. What determines which quantum processes give rise to space-time geometry? Why do the emergent equations take exactly the form that Einstein discovered? How do discrete quantum interactions create the illusion of continuous geometric curvature? The quantum foam continues its restless activity at scales too small for direct observation, potentially holding answers to questions that remain as mysterious today as they were when Einstein first proposed the geometric theory of gravity. The particles flicker in and out of existence, borrowing energy from the vacuum for infinitesimally brief moments before returning it with quantum mechanical precision. Somewhere in this probabilistic dance lies the origin of space-time itself, the quantum foundation from which gravity's illusion emerges. But the connection between quantum foam and classical geometry remains hidden, suspended between scales too small to observe and phenomena too large to ignore, humming with possibilities that consciousness cannot yet grasp. The galaxy spins too fast. Astronomers first noticed this problem in the 1970s, when careful measurements of stellar velocities revealed that stars in the outer regions of spiral galaxies orbit their galactic centers at speeds that should tear the structures apart. According to Newton's laws applied to the visible matter distributed throughout these cosmic pinwheels, the outer stars should move much more slowly or else escape entirely into intergalactic space. The Milky Way itself exhibits this peculiar behavior. Stars in our galaxy's outer spiral arms circle the galactic center at roughly 220 kilometers per second. Maintaining this velocity even at distances where the gravitational influence of visible matter should have weakened dramatically. If only ordinary matter contributed to galactic gravity, these distant stars should crawl along at less than a half their observed speeds, following the same mathematical relationships that govern planetary motion around the Sun. Vera Rubin's pioneering observations of the Andromeda Galaxy confirmed that this velocity anomaly represents a universal phenomenon rather than a local quirk of our own cosmic neighborhood. Galaxy after galaxy reveals the same pattern, rotation curves that remain flat rather than declining with distance, as if some invisible gravitational influence extends far beyond the regions where stars and gas clouds mark the boundaries of visible matter. The missing mass required to explain these observations dwarfs everything that telescopes can detect. Roughly 5 times more matter must exist in and around galaxies than appears in the form of stars, planets, gas clouds, and dust. This hypothetical dark matter interacts gravitationally with ordinary matter, its presence revealed through the orbital motions it influences, but remains invisible to electromagnetic radiation across the entire spectrum from radio waves to gamma rays. Computer simulations of galaxy formation and evolution require vast halos of dark matter to reproduce the structures observed throughout the universe. These invisible halos extend far beyond the visible edges of galaxies, creating gravitational scaffolding upon which ordinary matter accumulates into the spiral arms and elliptical distributions that telescopes reveal. Without dark matter's gravitational influence, galaxies could never have formed in the first place. let alone maintained their observed rotation patterns for billions of years. Yet the nature of this missing matter remains completely mysterious. Dark matter particles, if they exist, must interact extremely weakly with electromagnetic radiation, otherwise they would be detectable through their absorption or emission of light. They must also interact weakly with themselves, since dark matter appears to form smooth, extended halos rather than collapsing into dense concentrations like ordinary matter does when it radiates energy away through electromagnetic processes. Decades of increasingly sophisticated experiments have failed to detect dark matter particles directly. Underground laboratories shield detectors from cosmic radiation while searching for the rare collisions that might occur when dark matter particles encounter atomic nuclei. Particle accelerators attempt to create dark matter particles through high-energy collisions, hoping to observe their distinctive signatures among the debris of proton impacts. Space-based telescopes scan for the gamma rays that might be produced when dark matter particles annihilate with their antiparticles in regions of high dark matter density. But perhaps the problem lies not with missing matter, but with missing understanding of gravity itself. Modified Newtonian dynamics, or MOND, proposes that Newton's laws break down at the extremely low accelerations characteristic of galactic outskirts. In this alternative framework, gravitational effects become stronger than Newton predicts when accelerations fall below a critical threshold, roughly 10 circumflex 10 meters per second squared, about 100 billion times smaller than Earth's surface gravity. MOND reproduces galactic rotation curves with remarkable accuracy, using a single adjustable parameter to match observations across hundreds of different galaxies. The theory suggests that gravity behaves differently in the weak field regime that dominates galactic dynamics, transitioning from Newton's familiar inverse square law to a modified relationship that maintains stronger gravitational effects at large distances. This possibility raises profound questions about the fundamental nature of gravitational interaction. If gravity can deviate from Newton's laws under certain conditions, what other modifications might occur in extreme environments? Does general relativity itself require revision when applied to cosmic scales? Or do the field equations contain additional terms that become significant only in regimes far from those where the theory was originally tested? Some theoretical approaches attempt to explain MOND-like effects through modifications to Einstein's field equations, extrascalar fields, higher dimensional effects, or nonlinear relationships between matter density and spacetime curvature might all contribute to gravitational behavior that differs from general relativity's predictions. These modifications could arise naturally from quantum gravitational effects, string theory compactifications, or other fundamental physics that remains undiscovered. The dark matter versus modified gravity debate reflects deeper uncertainties about the relationship between observed phenomena and theoretical understanding. Both approaches make specific predictions that can be tested through careful observations, yet neither provides a completely satisfactory explanation for all gravitational anomalies observed on cosmic scales. Dark matter theories struggle to explain why the inferred mass distributions match so precisely the patterns predicted by MOND. Modified gravity theories have difficulty reproducing the gravitational lensing effects that seem to require actual mass concentrations in specific locations. Recent observations of galaxy collisions provide particularly compelling tests of these competing explanations. When galaxy clusters collide, ordinary matter interacts electromagnetically and becomes heated through friction and radiation, while dark matter, if it exists, should pass through the collision zone relatively unaffected. These events create situations where the gravitational effects inferred from stellar motions become separated from the distributions of ordinary matter visible through X-ray emissions from hot gas. The bullet cluster collision, observed in detail through multiple telescopes, shows exactly this predicted separation. Gravitational lensing measurements reveal mass concentrations that coincide with the colliding galaxies themselves, while X-ray observations show heated gas lagging behind in the collision wake. This spatial separation between gravitational effects and ordinary matter provides strong evidence for dark matter's existence as actual particles rather than modifications to gravitational law. Yet even this dramatic confirmation leaves fundamental questions unanswered. What are dark matter particles made of? Why do they interact so weakly with ordinary matter and electromagnetic radiation? How did the universe produce roughly 5 times more dark matter than ordinary matter during the Big Bang? The invisible scaffolding that shapes galactic structure remains as mysterious as it was when rotation curves first revealed its existence. The galaxy continues its ancient rotation, stars tracing elliptical orbits through dark matter halos that extend far beyond the visible spiral arms. Each stellar orbit follows geodesic paths through spacetime, curved by mass concentrations that remain invisible to every electromagnetic probe yet devised. Whether this curvature arises from exotic particles or modified gravitational laws, the fundamental mystery persists. Why does the universe hide its gravitational influence behind veils of invisibility that consciousness struggles to penetrate? The missing mass dreams in darkness, shaping cosmic structure through gravitational influence alone, while revealing nothing of its own nature to the electromagnetic radiation that carries information to curious observers. Galaxies spin through their invisible foundations, following orbital patterns that point toward deep truths about gravity's true character, truths that remain suspended between competing explanations, neither fully confirmed nor convincingly refuted by the accumulated evidence of careful observation. The event horizon shimmers at the boundary between knowledge and mystery, not a physical surface that objects can touch or penetrate, but a mathematical membrane in space-time where causality itself breaks down according to distant observers. Information that crosses this threshold appears to vanish forever, creating paradoxes that challenge the most fundamental assumptions about physical reality and the nature of existence itself. Stephen Hawking first recognized the profound implications in the 1970s when he applied quantum field theory to the curved space-time geometry around black holes. Virtual particle pairs, constantly emerging from quantum vacuum fluctuations, behave differently near event horizons than in empty space. When such pairs materialize just outside the horizon, one member might fall inward while the other escapes to infinity, converting borrowed vacuum energy into real particles through the black hole's gravitational field. This Hawking radiation carries energy away from the black hole, gradually reducing its mass through a process so slow that stellar mass black holes would require times far longer than the current age of the universe to evaporate completely. But the radiation appears to carry no information about the matter that originally formed the black hole or fell into it subsequently. Every black hole of the same mass, charge, and angular momentum produces identical Hawking radiation, regardless of what specific materials created it or what objects it has consumed. This leads to the information paradox that has puzzled physicists for decades. Quantum mechanics demands that information about physical systems can never be truly destroyed. It may become scrambled or dispersed. But the total amount of information in any isolated system must remain constant over time. Yet black holes seem to violate this principle by erasing all traces of the information contained in objects that cross their event horizons. The paradox becomes particularly acute when black holes evaporate completely through Hawking radiation. If the final burst of radiation carries no more information than any previous emission, then all the information that ever fell into the black hole disappears when the horizon finally shrinks to nothing. This would represent a fundamental violation of quantum mechanical principles, suggesting that either general relativity or quantum field theory must be modified to resolve the contradiction. One proposed solution involves the holographic principle, which suggests that all the information contained within any volume of space can be encoded on its two-dimensional boundary. In this framework, information about objects falling into black holes becomes stored on the event horizon itself, where it can potentially influence the properties of outgoing Hawking radiation. The black hole's interior might be a kind of holographic projection from patterns encoded on its surface. This holographic encoding implies that our familiar three-dimensional experience of space might itself be illusory, a projection from information stored on distant two-dimensional boundaries. The universe we inhabit could be analogous to a hologram, where all the information that creates our sense of depth and volume actually resides on surfaces we cannot directly perceive. Reality becomes a kind of cosmic illusion, with consciousness experiencing projections from hidden informational substrates. Modern research in string theory and quantum gravity supports various versions of the holographic principle. The ADS-CFT correspondence, discovered by Juan Maldacena, demonstrates exact mathematical relationships between gravitational theories in higher dimensional spaces and quantum field theories defined on their lower dimensional boundaries. These correspondences suggest that gravity itself might emerge from more fundamental quantum informational processes occurring on holographic surfaces. But the holographic solution to the information paradox requires that event horizons behave very differently from what general relativity predicts. Instead of smooth, empty regions where falling observers experience nothing unusual during their passage inward, horizons must somehow encode enormous amounts of information in their surface structure. This information must influence outgoing radiation in ways so subtle that they remain undetectable by current experimental techniques. The firewall paradox, proposed by Ahmed Al-Mahiri and colleagues, highlights contradictions in attempts to preserve information while maintaining other fundamental principles. If information is preserved through correlations between interior and exterior regions, then observers falling through event horizons should encounter walls of high-energy radiation rather than empty space. This prediction conflicts directly with the equivalence principle, which demands that freely falling observers experience no unusual effects when crossing horizons. These paradoxes suggest that the smooth space-time geometry described by Einstein's field equations might break down near black hole horizons, replaced by something far stranger than classical physics can describe: quantum gravitational effects, normally negligible except at Planck-scale energies, might become amplified near horizons through processes that remain beyond current theoretical understanding. Alternative approaches propose that black holes never actually form event horizons, but instead create frozen star configurations where matter approaches but never quite reaches the critical density required for horizon formation. In these models, information never becomes truly trapped because horizons never completely close. The apparent event horizons observed from distant perspectives represent asymptotic limits rather than actual causal boundaries. Yet other theories suggest that the information paradox arises from mistaken assumptions about the nature of time and causality near black holes. If time itself becomes emergent from more fundamental quantum processes, then the apparent loss of information might reflect limitations in how consciousness conceptualizes temporal evolution rather than genuine violations of physical law. The paradox extends beyond black holes to cosmological horizons and the fundamental structure of space-time itself. If the universe underwent rapid inflation during its earliest moments, then regions of space became causally disconnected, creating horizons that persist to the present day. Information about distant regions lies forever beyond our observational reach, trapped behind cosmic event horizons that expand with the accelerating universe. These cosmological horizons raise similar questions about information preservation and the holographic principle. Does all the information about our observable universe reside on its boundary surface, located roughly 46 billion light-years away? If so, what determines which information becomes accessible to conscious observers embedded within the holographic projection? The questions multiply without resolution, pointing toward gaps in understanding that may require completely new conceptual frameworks. Modern experiments attempt to test holographic principles through analog systems that simulate black hole physics in laboratory settings, sonic black holes in flowing fluids, optical black holes in nonlinear materials, and quantum simulators using ultra-cold atomic gases all provide controlled environments where information flow across event horizons can be studied in detail. These systems might reveal whether information is truly lost or simply encoded in ways too subtle for direct observation. But perhaps the deepest mystery lies in the question of why information should be preserved at all. The quantum mechanical demand for information conservation emerges from mathematical principles, unitarity, reversibility, the structure of Hilbert spaces, that may not apply to gravitational systems where spacetime geometry itself becomes dynamical. If gravity is indeed geometric rather than force-like, then information preservation might be yet another classical concept that breaks down when applied beyond its legitimate domain. The event horizon continues its patient existence at the boundary between knowledge and ignorance, encoding secrets that may be fundamentally inaccessible to consciousness embedded within classical spacetime, whether those secrets concern missing information, holographic projections, or the illusory nature of three-dimensional reality itself. They remain suspended at the threshold where quantum mechanics meets general relativity, humming with possibilities that understanding cannot yet resolve. Temperature emerges, not from any fundamental particles or forces, but from the statistical behavior of countless atoms moving in random directions at various speeds, the sensation of heat that consciousness recognizes, the warmth of sunlight on skin, the chill of winter air, the scalding touch of boiling water, arises from collective molecular motion averaged over scales vastly larger than individual particles. No single atom possesses temperature. Individual molecules carry kinetic energy as they bounce through space, colliding with neighbors and exchanging momentum through electromagnetic interactions. But temperature represents something entirely different, a statistical property that emerges when enormous numbers of particles reach thermal equilibrium, the individual energies distributed according to patterns that statistical mechanics describes with mathematical precision. This emergence of macroscopic properties from microscopic interactions provides a template for understanding how other, seemingly fundamental phenomena might arise from more basic processes, just as temperature emerges from molecular motion without being reducible to the behavior of any individual particle. Gravity might emerge from quantum interactions without being encoded in the properties of specific particles or fields. Eric Verlinde proposed exactly this possibility in his entropic gravity theory, suggesting that gravitational force arises from the tendency of systems to maximize their entropy, the statistical measure of disorder or information content. In this framework, what appears as gravitational attraction represents nothing more than the universe's preference for configurations that maximize the number of possible microscopic arrangements consistent with observed macroscopic conditions. The argument begins with the holographic principle, which suggests that all information contained within any volume of space can be encoded on its two-dimensional boundary. This encoding implies that three-dimensional space itself might be emergent rather than fundamental, constructed from information stored on distant surfaces in ways analogous to how temperature emerges from molecular statistics. If space is emergent, then the equations governing motion through space, including Einstein's field equations for gravity, must also be emergent phenomena rather than fundamental laws. Just as thermodynamics emerges from statistical mechanics without requiring new fundamental forces, general relativity might emerge from quantum information theory without requiring gravitons or other gravitational particles. Verlin's calculations demonstrate that Newton's law of universal gravitation follows naturally from holographic principles combined with basic thermodynamic relationships. When objects approach holographic boundaries, they displace information in ways that create entropic forces directing them toward configurations of maximum entropy. These forces reproduce gravitational attraction without requiring any fundamental gravitational interaction. The approach extends to Einstein's field equations, which emerge as thermodynamic relationships between energy, entropy, and information storage on holographic surfaces. Spacetime curvature represents the geometric manifestation of entropic gradients created by matter and energy distributions. Massive objects curve spacetime not through some mysterious coupling between matter and geometry, but because their presence affects information storage patterns on holographic boundaries. This entropic picture resolves several puzzles that plague traditional approaches to quantum gravity. If gravity emerges from quantum information rather than representing a fundamental interaction, then the problems of renormalizing gravitational field theories disappear. There are no gravitons to quantize, no infinite quantities to subtract away, no need to unify gravity with other fundamental forces through grand unified theories or theories of everything. The approach also provides natural explanations for dark matter and dark energy phenomena. If gravity emerges from entropic forces, then modifications to gravitational behavior might arise naturally when systems approach the holographic bounds imposed by finite information storage capacity. The flat rotation curves observed in galaxies might reflect entropic effects that become significant when gravitational accelerations approach fundamental limits related to the universe's information content. But emergent gravity faces serious challenges when confronted with detailed observational tests. The theory reproduces Newton's laws and Einstein's field equations only in specific limits where thermodynamic equilibrium assumptions remain valid. Dynamic situations involving rapid changes in gravitational fields or strong field regimes near black holes and neutron stars require extensions that have not yet been successfully developed. The emergence paradigm also raises profound questions about the relationship between microscopic and macroscopic descriptions of physical reality. Temperature emerges from molecular motion through statistical averaging over enormous numbers of particles, but consciousness never experiences individual molecular impacts directly. Similarly, if gravity emerges from quantum information, what prevents conscious observers from detecting the underlying quantum processes directly? Modern research in quantum information theory reveals deep connections between entanglement, geometry, and thermodynamics that support various versions of emergent gravity. The Ryu-Takayanagi correspondence shows how quantum entanglement between different regions of space determines the geometric relationships between those regions. More entanglement corresponds to closer geometric proximity, suggesting that spatial distance itself emerges from patterns of quantum correlation. These entanglement geometry correspondences provide specific mechanisms through which emergent spacetime might arise from more fundamental quantum processes. Space becomes a kind of quantum error-correcting code, with geometric relationships encoding information about quantum correlations in ways that remain stable against small perturbations. Gravity emerges as the force required to maintain these geometric relationships when matter and energy perturb the underlying quantum information. Yet the emergence picture encounters difficulties when applied to cosmological observations. If gravity emerges from quantum information stored on holographic boundaries, what determines the location and properties of those boundaries? Why does the universe appear to have the specific informational structure required to produce Einstein's field equations, rather than some other set of geometric relationships? The cosmological constant problem becomes particularly acute in emergent approaches. Dark energy, inferred from observations of cosmic acceleration, requires a vacuum energy density that differs from quantum field theory, predictions by more than 120 orders of magnitude. If gravity emerges from quantum information, why doesn't this emergence process produce the enormous cosmological constant that quantum mechanics seems to demand? Perhaps the answer lies in recognizing that emergence itself occurs at multiple levels throughout the hierarchy of physical description, just as temperature emerges from molecular motion, and molecular motion emerges from atomic interactions, and atomic interactions emerge from quantum field dynamics. Gravity might represent just one level in an infinite regress of emergent phenomena. Each level appears fundamental when viewed from appropriate scales, but reveals its emergent character when examined from perspectives that encompass larger or smaller domains. The patterns continue their statistical dance. Individual quantum events averaging into classical fields combining into geometric structures organizing into the spacetime stage upon which cosmic drama unfolds. Somewhere in this hierarchy of emergence, consciousness finds itself embedded, experiencing gravity as a force while the universe maintains its deeper statistical secrets. The temperature of existence rises from quantum foam too fine for direct observation, warming space-time into the familiar illusions that support the emergence of awareness itself. The dimensions curl inward, not visible dimensions like length, width, and height that consciousness directly experiences, but hidden spatial directions so thoroughly compacted that they remain invisible even to the most sensitive instruments yet devised. String theory proposes that our familiar three-dimensional space represents only a tiny fraction of reality's full geometric structure, with 6 or 7 additional dimensions rolled up into configurations smaller than the smallest measurable distances. Every point in ordinary space harbours these extra dimensions, folded into complex geometric shapes called Calabi-Yau manifolds, that possess mathematical properties allowing them to remain stable across cosmic time, like viewing a garden hose from a great distance, where it appears one-dimensional despite actually having circular cross-sections. Our perspective on the universe reveals only the large-scale dimensions while missing the intricate internal structure that exists at every location. This hidden geometry provides a natural explanation for gravity's relative weakness compared to other fundamental forces. Electromagnetic interactions bind atoms together with forces trillions of times stronger than gravitational attraction between the same particles. Nuclear forces prove stronger still, capable of releasing enormous energies when atomic nuclei undergo fusion or fission, yet gravity, despite governing cosmic structure from planetary orbits to galactic clusters, barely affects individual atoms or molecules. In string theory's framework, this hierarchy of force strengths arises because gravity alone can propagate through all the hidden dimensions, while other forces remain confined to our familiar three-dimensional space. Gravitational effects spread their influence across the full higher dimensional space. becoming diluted compared to electromagnetic and nuclear forces that concentrate their effects within the lower dimensional surfaces where ordinary matter resides. The mathematics of string theory treats fundamental particles not as point-like objects, but as one-dimensional vibrating loops moving through the full higher dimensional space. Different vibrational patterns correspond to different particle types. Electrons, quarks, photons, and even hypothetical gravitons all emerge as distinct oscillation modes of the same underlying string-like entities. The apparent diversity of fundamental particles reduces to variations in vibrational frequency, like different musical notes produced by plucking the same guitar string. Gravitons in this picture represent the simplest possible vibrational pattern, strings oscillating in their fundamental mode without internal twists or complex harmonics. This simplicity allows gravitons to propagate freely through all dimensions of the higher dimensional space. While more complex vibrational patterns corresponding to other particles become trapped within lower dimensional surfaces by mechanisms analogous to quantum confinement in atomic systems, the extra dimensions must be compactified, curved back upon themselves in ways that prevent infinite extension, to avoid conflicts with observations that reveal no evidence for large-scale departures from three-dimensional geometry. Various compactification schemes produce different low-energy physics, leading to a vast landscape of possible string theories with different particle spectra and force strengths. Some estimates suggest that this landscape contains more than 10 circumflex 500 distinct vacuum states, each corresponding to a different possible universe with its own physical constants and particle interactions. This enormous multiplicity raises profound questions about why our universe exhibits the specific combination of forces, particles, and constants that we observe. If string theory admits so many possible configurations, what mechanism selects the particular vacuum state that gives rise to the standard model of particle physics plus general relativity? Some theorists propose that all possible vacuum states actually exist simultaneously in different regions of an infinite multiverse, with conscious observers finding themselves in regions compatible with their own existence through anthropic selection effects. But the extra dimensions remain stubbornly hidden from direct observation. Particle accelerators probe the structure of matter down to distances approaching 10 circumflex 18 meters, far smaller than atomic nuclei, yet reveal no evidence for additional spatial dimensions or the stringy structure that should become apparent at these scales. The compactification radius must be smaller than current experimental resolution, pushing the characteristic scale of string physics beyond the reach of foreseeable technology. Indirect tests attempt to detect signatures of extra dimensions through their effects on known physics. If gravity can leak into hidden dimensions, then gravitational attraction should deviate from Newton's inverse square law at distances comparable to the compactification scale. Precision measurements of gravitational forces between test masses separated by micron-scale distances search for such deviations, placing increasingly stringent limits on the size of possible extra dimensions. Large extra dimensions, if they exist, might also affect the behavior of high-energy particles produced in cosmic ray interactions or particle accelerator experiments. Particles with sufficient energy could escape into the hidden dimensions, carrying away momentum and energy in ways that would be detectable as missing energy in carefully balanced collision experiments. Current observations place limits on such effects that constrain possible extra-dimensional scenarios while not completely ruling them out. The landscape problem reflects a deeper tension between mathematical elegance and empirical specificity that pervades modern theoretical physics. String theory provides a mathematically consistent framework for unifying all fundamental forces, including gravity, within a single theoretical structure. Yet this unification comes at the cost of enormous complexity, with the theory's predictions depending sensitively on details of higher dimensional geometry that remain beyond experimental reach. Some physicists argue that this inaccessibility represents a fundamental limitation rather than a temporary technical obstacle. If the compactification scale lies near the Planck length, the scale where quantum gravitational effects become important, then direct exploration of extra dimensions would require energies comparable to those present during the Big Bang itself. Such energies exceed any conceivable experimental capability by factors of trillions or more. Alternative approaches to quantum gravity avoid extra dimensions entirely, attempting to explain gravitational phenomena through modifications to lower dimensional physics. Loop quantum gravity, causal set theory, and emergent gravity scenarios all work within familiar three-dimensional space, while proposing that space-time itself possesses discrete or emergent properties that become apparent only under extreme conditions. Yet the mathematical beauty of higher dimensional string theory continues to attract theoretical development despite its empirical elusiveness. The theory's internal consistency constraints lead to deep insights about the relationships between geometry, topology, and physics that prove valuable even if the extra dimensions themselves remain unobservable. Mirror symmetry, black hole entropy calculations, and holographic correspondences all emerge from string-theoretic research and now find applications throughout theoretical physics. The hidden dimensions continue their patient existence, curled into geometric configurations too small for consciousness to perceive directly. Every breath draws in air molecules that move through space threaded with invisible directions. Every step carries bodies through regions where gravity weakens as it spreads across inaccessible dimensions. The familiar three-dimensional world floats like a surface on an ocean of hidden geometry, supported by mathematical structures that may determine the fundamental constants and forces that govern physical reality. Whether these extra dimensions represent actual features of the universe, or artifacts of theoretical models that have grown too complex for empirical validation, remains one of the deepest mysteries in contemporary physics. The strings vibrate through their higher dimensional spaces, producing the particles and forces of the familiar world while keeping their own geometric secrets suspended between mathematical necessity and observational absence. The vacuum energy hums. Quantum field theory predicts that empty space seethes with virtual particle pairs, zero-point oscillations, and vacuum fluctuations that contribute an enormous background energy density throughout the universe. These quantum mechanical effects should curve space-time dramatically, creating a cosmological constant millions of times larger than what astronomical observations actually reveal. The discrepancy represents perhaps the most severe failure of theoretical prediction in the history of physics. When physicists calculate the vacuum energy density using standard quantum field theory techniques, they obtain values around 10 circumflex 120 times larger than the dark energy density inferred from observations of cosmic acceleration. This mismatch between theory and observation spans more than 100 orders of magnitude, a disagreement so profound that it suggests fundamental misunderstandings about the nature of quantum mechanics, general relativity, or both. Albert Einstein first introduced the cosmological constant in 1917 as a modification to his field equations, adding a term that could balance gravitational attraction and allow for static universe models that neither expanded nor contracted. When Edwin Hubble's observations revealed that the universe actually expands, Einstein abandoned the cosmological constant, reportedly calling it his greatest mistake. Yet the mathematical term remained in the field equations, waiting for observational evidence that might reveal its physical significance. That evidence arrived in 1998 through supernova, observations that revealed the expansion of the universe to be accelerating rather than slowing down under gravitational influence. Type Ia supernovae, which serve as standardizable candles for measuring cosmic distances, appeared fainter than expected at high redshifts, indicating that they lie farther away than conventional cosmological models predicted. The universe must be expanding faster now than in the past, driven by some form of dark energy with repulsive gravitational effects. The simplest explanation for this cosmic acceleration invokes Einstein's cosmological constant, now interpreted as representing the energy density of empty space itself. In this picture, vacuum quantum fluctuations contribute a constant energy density throughout space-time, creating negative pressure that drives accelerated expansion. The cosmological constant becomes a measure of how much energy is stored in the quantum mechanical ground state of all fields. But quantum field theory calculations of this ground state energy yield results that violate observational constraints by factors so enormous that they challenge the conceptual foundations of both theories. If vacuum fluctuations really contribute to space-time curvature according to Einstein's field equations, then the universe should have collapsed or expanded catastrophically long before stars and galaxies could form. The observed cosmic acceleration requires dark energy densities that are fantastically small compared to quantum theoretical predictions. Various mechanisms have been proposed to resolve this cosmological constant problem, but none have achieved widespread acceptance. Supersymmetry might arrange for positive and negative contributions to vacuum energy to cancel with extraordinary precision, leaving only tiny remainders that could account for observed dark energy densities. Extra dimensions might dilute vacuum energy effects by spreading them across higher dimensional spaces, reducing their impact on four-dimensional space-time curvature. The anthropic principle suggests that the cosmological constant takes its observed value not through fundamental physical mechanisms, but through selection effects in a multiverse containing regions with different vacuum energy densities. Only universes with cosmological constants small enough to permit structure formation to develop conscious observers capable of measuring their own cosmic parameters. This explanation replaces dynamical mechanisms with statistical arguments about observer selection in infinite ensembles of possible universes, but anthropic reasoning raises uncomfortable questions about the relationship between physical law and conscious observation. If fundamental constants are determined by observer selection rather than underlying dynamics, what distinguishes physics from pure statistical accident? Why should the universe care about the existence of conscious observers when determining its basic parameters? The anthropic approach explains the cosmological constant's value, while undermining confidence in the predictive power of theoretical physics. Alternative approaches propose that the cosmological constant problem reveals fundamental limitations in current theoretical frameworks, rather than indicating fine-tuning or anthropic selection. If gravity emerges from more basic quantum information processes, then vacuum energy might not contribute to space-time curvature in the ways that naive calculations suggest. The relationship between quantum field theory and general relativity might break down precisely in regimes where vacuum fluctuations approach the scale of cosmic acceleration. Modified gravity theories attempt to explain cosmic acceleration without invoking dark energy or vacuum energy contributions. Scalar field modifications, higher derivative gravity theories, and extra-dimensional models all propose that gravitational dynamics itself changes on cosmic scales in ways that produce apparent acceleration without requiring negative pressure sources. These approaches treat the cosmological constant problem as a symptom of incomplete understanding of gravitational physics, rather than a crisis in quantum field theory. Yet observational evidence continues to support the simplest dark energy models based on a positive cosmological constant, with density approximately 7x10 circumflex 30 grams per cubic centimeter. This incredibly tiny energy density, equivalent to roughly 6 hydrogen atoms per cubic meter, drives the acceleration that will eventually carry distant galaxies beyond our observational horizon as space expands faster than light can travel between increasingly separated regions. The precision with which this dark energy density matches theoretical expectations for vacuum energy contributions from quantum fields remains a profound mystery. The match is neither exact enough to confirm theoretical understanding nor different enough to rule out connections entirely. The cosmological constant sits precariously between triumph and failure of fundamental physics, accurately describing cosmic acceleration while defying theoretical explanation. Modern surveys of cosmic structure attempt to determine whether dark energy properties remain constant over cosmic time or evolve according to scalar field dynamics that might reveal its fundamental nature. Measurements of cosmic microwave background radiation, supernova distances, galaxy clustering patterns, and gravitational lensing effects all provide complementary probes of dark energy behavior across different cosmic epochs and distance scales. But the observations remain consistent with the simplest possible model, a cosmological constant that maintains fixed energy density as space expands, neither diluting like ordinary matter nor changing properties over cosmic time. This constancy suggests deep connections to the vacuum structure of quantum field theory, yet the predicted magnitude remains impossibly large compared to observational requirements. The quantum vacuum continues its restless activity, virtual particles appearing and disappearing in patterns that quantum field theory describes with mathematical precision. Each cubic centimeter of empty space harbors enough theoretical vacuum energy to power human civilization for longer than the current age of the universe. Yet this enormous energy density remains completely hidden from gravitational detection. The cosmological constant sleeps at the boundary between quantum mechanics and general relativity, neither fully explained by current understanding nor entirely disconnected from the theoretical frameworks that govern physical reality. Perhaps the answer lies in recognizing that the vacuum itself represents another layer of illusion, a concept that applies only within limited domains where classical field theory provides adequate approximations. If spacetime geometry emerges from more fundamental quantum information processes, then vacuum energy might be a derived concept rather than a fundamental ingredient in cosmic evolution. The universe accelerates according to its own hidden logic, while consciousness struggles to reconcile the elegant mathematics of quantum fields with the patient expansion of cosmic space itself. The velocities refuse to decline. In galaxy after galaxy, astronomers measure stellar orbital speeds that violate the expectations of Newtonian mechanics when applied to visible matter alone. Stars in the outer regions of spiral galaxies circle their galactic centers at nearly constant speeds, maintaining orbital velocities of hundreds of kilometers per second even at distances where conventional gravity should have weakened to negligible levels. This flat rotation curve phenomenon extends far beyond the visible edges of galactic disks, into regions where no stars shine and no gas clouds emit detectable radiation. Radio telescopes tracking neutral hydrogen clouds in these outer territories reveal the same pattern: orbital velocities that remain stubbornly high instead of declining with distance according to Kepler's laws. Something invisible maintains gravitational influence far beyond the reach of observable matter. Mordechai Milgram first proposed an alternative explanation in 1983, suggesting that Newton's laws themselves might require modification when applied to systems with extremely low accelerations. His modified Newtonian dynamics, or MOND, introduces a critical acceleration scale below which gravitational effects become stronger than Newton's inverse square law predicts. This modification reproduces galactic rotation curves without requiring invisible dark matter. The critical acceleration that MOND introduces, approximately 1.2 x 10 circumflex 10 meters per second squared, appears throughout cosmic structure formation in ways that seem too precise for coincidence. This value equals roughly 1/10,000,000th of Earth's surface gravity, marking the boundary between regimes where Newtonian mechanics works perfectly and regions where gravitational effects require modification. Stars orbiting within galactic centers experience accelerations above this threshold and follow Newtonian predictions exactly, while outer regions with accelerations below the critical value show enhanced gravitational effects. The acceleration scale also connects to fundamental cosmological parameters in unexpected ways. The critical MOND acceleration approximately equals the speed of light times the Hubble constant divided by 2p, linking galactic dynamics to the expansion rate of the universe itself. This relationship suggests that MOND might reflect deep connections between local gravitational physics and global cosmic structure rather than representing an ad hoc modification to explain specific observations. MOND's empirical successes extend far beyond the rotation curve observations that motivated its development. The theory predicts the surface brightnesses of elliptical galaxies, the velocity dispersions of globular cluster systems, and the internal dynamics of galaxy clusters with remarkable accuracy. Many of these predictions were made before the relevant observations became available, demonstrating genuine predictive power rather than mere retroactive fitting to known data. The Tully-Fisher relation, which connects galactic rotation velocities to total luminosities, emerges naturally from MOND dynamics without requiring fine-tuning or additional assumptions. In Newtonian gravity, this relationship requires careful conspiracy between dark matter distributions and stellar mass-to-light ratios to maintain the observed correlations across different galaxy types. MOND reproduces the same correlations through the direct connection between acceleration modifications and observable matter distributions, but MOND faces serious challenges when applied to larger cosmic structures where general relativistic effects become important. The theory was originally formulated as a modification to Newton's laws, making it difficult to extend consistently to general relativistic contexts where space-time curvature itself becomes dynamical. Various attempts to create relativistic versions of MOND have been proposed, but none achieve the elegance and simplicity of the original Newtonian formulation. Tensor vector scalar gravity theories attempt to embed MOND-like effects within a fully relativistic framework by introducing additional fields beyond the metric tensor that describes space-time curvature in Einstein's theory. These extra fields interact with matter in ways that modify gravitational dynamics at low accelerations while preserving general relativity's successes in high acceleration regimes. But the resulting theories often contain multiple free parameters and complex field interactions that reduce their predictive power. The most successful relativistic MOND theories reproduce Einstein's field equations in strong field limits while generating MOND-like behavior when gravitational accelerations fall below the critical threshold. These theories predict specific signatures in gravitational wave emissions from binary systems, light deflection around galaxies, and cosmic microwave background radiation patterns that could potentially distinguish them from dark matter models through precise observations. Yet MOND struggles to explain several phenomena that dark matter theories handle naturally. The collision dynamics of galaxy clusters, particularly the famous bullet cluster system, show spatial separations between gravitational effects inferred from lensing and ordinary matter distributions revealed through X-ray observations. Dark matter theories explain this separation as evidence for collisionless dark matter particles that pass through collision zones, while ordinary matter interacts electromagnetically and becomes heated. Mond-based explanations for cluster collisions require additional assumptions about the behavior of modified gravity in highly dynamic situations, or invoke phantom dark matter components that interact even more weakly than conventional dark matter candidates. These modifications compromise Mond's original appeal as a theory that eliminates the need for invisible matter entirely. The cosmic microwave background radiation also presents challenges for Mond theories. The acoustic oscillation patterns frozen into this ancient light reflect the interplay between gravitational attraction, radiation pressure, and baryonic matter during the universe's first few 100,000 years. Dark matter theories reproduce these patterns by invoking collisionless particles that enhance gravitational clustering without participating in electromagnetic interactions that drive acoustic oscillations. Mond theories must explain the same acoustic signatures through modifications to gravitational dynamics alone. Without the benefit of additional matter components, some relativistic Mond models achieve reasonable fits to cosmic microwave background data, but they typically require additional fields or interactions that reduce the theory's elegance compared to its Newtonian predecessor. The primordial nuclear synthesis constraints provide another test of modified gravity approaches. The abundances of light elements produced during the universe's first few minutes depend sensitively on the expansion rate during that epoch, which in turn depends on the total energy density including all forms of matter and radiation. Dark matter contributes to this energy density in ways that affect nuclear synthesis predictions. While Mond modifications might alter the relationship between matter content and expansion dynamics, current observations of light element abundances favor cosmological models that include significant dark matter components, though the constraints are not precise enough to rule out all Mond-based alternatives completely. Future observations of primordial deuterium and helium abundances might provide more stringent tests of whether modified gravity alone can account for both galactic dynamics and cosmic structure formation. The debate between dark matter and modified gravity reflects deeper questions about the relationship between theoretical elegance and empirical adequacy in physics. Dark matter theories preserve the mathematical structure of general relativity, while invoking new particles that remain undetected despite decades of increasingly sophisticated searches. Mond theories modify well-tested gravitational laws while achieving remarkable empirical success in explaining galactic observations without additional matter components. Perhaps both approaches capture partial truths about gravitational physics without providing complete pictures of the underlying reality. Dark matter might exist while gravitational dynamics also require modification at cosmic scales. Alternatively, the apparent need for both dark matter and modified gravity might signal that current theoretical frameworks miss essential features of how gravity operates in regimes far from those where general relativity was originally tested. The search for direct dark matter detection continues in underground laboratories around the world, using increasingly sensitive detectors to search for collisions between hypothetical dark matter particles and atomic nuclei. Meanwhile, precision tests of gravitational dynamics probe the boundaries where Mond modification should become apparent, measuring gravitational forces and accelerations with ever-improving accuracy. The galactic rotation curves continue their flat trajectories, stellar orbits tracing paths that require either invisible matter or modified physics to explain their observed properties. Whether the universe hides 5/6 of its matter content in exotic particles, or reveals the limitations of current gravitational theory through these velocity anomalies. The mystery persists at the intersection between observation and understanding, where familiar physics encounters phenomena that stretch theoretical frameworks beyond their demonstrated domains. The threads weave, not visible strands that fingers might grasp or eyes perceive, but quantum mechanical correlations that connect particles across arbitrary distances with no apparent mechanism for information transfer. Einstein called this spooky action at a distance. Dismissing entanglement as an unphysical artifact of incomplete theoretical understanding, yet decades of increasingly precise experiments confirm that quantum entanglement represents a fundamental feature of reality rather than a mathematical curiosity. When two particles become quantum entangled, their properties remain correlated regardless of the spatial separation between them. Measuring the spin of one electron in a laboratory on Earth instantly determines the spin of its entangled partner, even if that partner has travelled to distant galaxies. The correlation appears instantaneous, transcending the speed of light limitations that constrain all other forms of communication and interaction in the universe. This instantaneous correlation does not violate relativity, because no information can be transmitted through entanglement alone. The measurement results on each particle appear random when considered individually, gaining their correlated character only when compared across both locations. Conscious observers cannot use entanglement to send messages faster than light, but they can verify that some form of non-local connection persists between quantum systems that have interacted in the past. Modern theoretical physics suggests that these quantum correlations might provide the fundamental substrate from which space-time geometry itself emerges. If space and time represent emergent properties arising from patterns of quantum entanglement, then the mysterious spooky action that Einstein rejected might be the mechanism through which gravitational phenomena acquire their geometric character. The Ryuta-Kayanagi correspondence, discovered in the context of holographic theories, demonstrates precise mathematical relationships between quantum entanglement entropy and geometric area in higher dimensional spacetimes. Regions that share more quantum entanglement correspond to shorter geometric distances in emergent spatial structures, while regions with less entanglement become geometrically separated by larger distances. This entanglement geometry correspondence suggests that the familiar three-dimensional space through which objects move might be a kind of quantum error-correcting code, with spatial relationships encoding information about underlying entanglement patterns in ways that remain stable against small perturbations. Gravity emerges as the force required to maintain these geometric relationships when matter and energy distributions perturb the quantum correlations that give rise to spatial structure. In this picture, massive objects do not curve pre-existing spacetime through some mysterious coupling between matter and geometry. Instead, matter and energy affect the entanglement patterns from which spacetime emerges, causing the geometric relationships to adjust in ways that produce the phenomena we interpret as gravitational attraction. Space itself becomes a derived concept rather than a fundamental arena within which physics unfolds. The implications extend to black holes, where entanglement physics might resolve the information paradox that has puzzled physicists for decades. If black hole interiors and exteriors remain connected through quantum entanglement, then information falling into black holes never truly disappears but instead becomes encoded in correlations that span the event horizon. The apparent loss of information reflects limitations in how classical observers can access quantum correlations, rather than genuine destruction of information. But emergent spacetime scenarios raise profound questions about the relationship between quantum mechanics and conscious observation. If space and time emerge from entanglement patterns, What determines which entangled states give rise to the specific geometric structure that conscious observers experience? Why does the emergent geometry take exactly the form described by Einstein's field equations, rather than some other mathematical relationship? The quantum error correction analogy provides partial answers by suggesting that only certain entanglement patterns remain stable against the decoherence effects that inevitably affect quantum systems interacting with their environments. Spacetime geometry might represent the classical limit of quantum entanglement patterns that can maintain coherence over cosmic scales and time periods. Alternative geometric structures might be possible in principle, but unstable against environmental perturbations. Experimental tests of emergent spacetime theories remain beyond current technological capabilities because the relevant quantum correlations operate at energy scales approaching the Planck length, where quantum gravitational effects become important. Direct detection of the quantum entanglement that supposedly underlies spacetime structure would require probes sensitive to correlations between regions separated by distances smaller than any measurable scale. Indirect tests attempt to detect signatures of emergent spacetime through its effects on known physics. If space and time are emergent rather than fundamental, then violations of locality and causality might become apparent under extreme conditions where the emergent description breaks down. Precision measurements of particle interactions at high energies search for such violations, placing increasingly stringent limits on the scale where emergent effects might become detectable. The holographic principle suggests that the emergence of space-time from entanglement might be observable through the relationship between bulk physics and boundary dynamics in gravitational systems. Anti-de Sitter spacetimes with conformal field theory boundaries provide exactly solvable examples where bulk gravitational physics corresponds precisely to boundary quantum field theory without gravity. These correspondences demonstrate that gravitational phenomena can emerge from non-gravitational quantum dynamics in specific geometric configurations. But extending these holographic correspondences to realistic cosmological situations remains an unsolved challenge. Our universe appears to have positive cosmological constant and asymptotically de Sitter geometry, rather than the negative cosmological constant required for anti-de Sitter constructions. Whether emergent spacetime scenarios can reproduce the observed cosmic acceleration and structure formation remains an open question. The relationship between quantum entanglement and classical geometry also encounters difficulties when applied to the quantum measurement problem. If conscious observers exist within emergent spacetime, how do their observations affect the entanglement patterns from which space and time emerge? Does the act of measurement cause quantum correlations to collapse in ways that modify spacetime geometry itself? Some approaches suggest that consciousness plays a fundamental role in selecting which entanglement patterns become realized as classical spacetime, making observers active participants in determining the geometric structure of reality, rather than passive recipients of pre-existing spatial relationships. This possibility pushes the mystery of gravitational emergence into the even deeper mystery of consciousness and its relationship to quantum mechanical phenomena. The quantum threads continue their invisible weaving, correlating particle properties across cosmic distances while maintaining the patterns of entanglement that might give rise to the three-dimensional space through which consciousness moves. Whether these correlations represent the fundamental substrate from which gravity emerges or simply another layer of illusion built upon deeper quantum mechanical mysteries, they persist at the boundary between local observation and global structure, connecting individual measurements to cosmic geometry through mechanisms that remain suspended between theoretical possibility and empirical confirmation. Information falls inward, not data in the familiar sense of books or computer files, but the quantum mechanical specification of every property that distinguishes one physical system from another. This information appears to vanish completely when it crosses a black hole's event horizon, creating paradoxes that challenge the most fundamental principles of quantum mechanics and thermodynamics. The paradox begins with Stephen Hawking's discovery that black holes emit thermal radiation with temperatures inversely proportional to their masses. This Hawking radiation carries energy away from black holes, causing them to shrink slowly through evaporation processes that should eventually eliminate them completely. But the radiation appears to carry no information about the specific matter that formed the black hole or fell into it during its lifetime. Every black hole of the same mass, electric charge, and angular momentum produces identical Hawking radiation, regardless of whether it formed from collapsed hydrogen, iron, antimatter, or any other material. The no-hair theorem of general relativity states that black holes possess only these three conserved quantities, with all other information about their formation erased by the gravitational collapse process that created the event horizon. This erasure of information violates the fundamental principles of quantum mechanics, which demand that the total amount of information in any isolated system must remain constant over time. Quantum mechanical evolution proceeds through unitary transformations that preserve information even when they scramble it beyond practical recognition. The apparent destruction of information by black holes suggests either that quantum mechanics breaks down in gravitational contexts, or that general relativity requires modification. The paradox becomes particularly acute during the final stages of black hole evaporation. As black holes shrink through Hawking radiation, their temperatures increase and their evaporation rates accelerate. The final burst of radiation should carry away the last remnants of the black hole's mass energy. But general relativity provides no mechanism for this radiation to carry information about everything that ever fell through the event horizon. If information is truly destroyed during black hole evaporation, then pure quantum states can evolve into mixed states, violating the reversibility that underlies all quantum mechanical calculations. This would require fundamental modifications to quantum theory that might affect every physical process, not just exotic phenomena involving black holes and strong gravitational fields. Various proposals attempt to resolve the information paradox without abandoning either quantum mechanics or general relativity. The holographic principle suggests that information about objects falling into black holes becomes encoded on the event horizon itself, where it can potentially influence the properties of outgoing Hawking radiation. In this picture, the black hole's interior might be a holographic projection from patterns stored on its two-dimensional surface. But holographic encoding requires that event horizons possess internal structure capable of storing enormous amounts of information. A black hole with the mass of our Sun would need to encode roughly 10 circumflex 66 bits of information on its horizon surface to preserve all the quantum information of the matter from which it formed. This information density approaches the theoretical maximum allowed by quantum mechanics, suggesting that event horizons operate at the absolute limits of information storage capacity. The firewall paradox, discovered by Ahmed Almheri and colleagues, reveals contradictions between information preservation and other fundamental principles. If information falling into black holes remains correlated with outgoing Hawking radiation to preserve unitarity, then observers falling through event horizons should encounter walls of high-energy radiation rather than the empty space predicted by general relativity. This conflicts with the equivalence principle, which demands that freely falling observers experience nothing unusual when crossing horizons. Some theorists propose that black holes never actually form complete event horizons, but instead create fuzzballs or gravastars, exotic objects that superficially resemble black holes while avoiding true horizon formation. These alternatives preserve information by preventing it from ever reaching regions where it might be permanently trapped, but they require modifications to general relativity that have not been observationally confirmed. The ER equals sign EPR correspondence, proposed by Juan Maldacena and Leonard Susskind, suggests deep connections between quantum entanglement and space-time geometry that might resolve information paradoxes. In this framework, Einstein-Rosen bridges, wormholes connecting distant regions of spacetime, represent the geometric manifestation of Einstein-Podolsky-Rosen correlations, quantum entanglement between separated particles. If entangled particles remain connected through microscopic wormholes, then information falling into black holes might escape through quantum tunneling effects that operate via these geometric connections. The black hole interior and exterior remain linked through quantum entanglement that manifests as spatial connectivity, allowing information to flow between regions that appear causally disconnected in classical general relativity. But wormhole-based solutions to the information paradox encounter their own difficulties. Traversable wormholes typically require exotic matter with negative energy density to remain stable against collapse. Such matter violates the classical energy conditions that underlie many theorems in general relativity, raising questions about whether wormhole geometries can exist in realistic physical situations. The quantum error correction properties of holographic theories provide another avenue for resolving information paradoxes. If spacetime geometry emerges from quantum error correcting codes, then information falling into black holes might be encoded redundantly across multiple degrees of freedom in ways that allow reconstruction, even when some information channels become inaccessible. This error correction perspective suggests that the apparent loss of information in black holes reflects limitations of classical observers rather than genuine information destruction. Quantum information might remain accessible through non-local correlations that transcend the causal structure imposed by classical space-time geometry. The information exists, but cannot be accessed using classical retrieval methods that respect locality and causality constraints. Modern experiments attempt to test information preservation principles through analog black hole systems created in laboratory settings, sonic black holes in flowing fluids, optical black holes in nonlinear materials, and quantum simulators using ultra-cold atomic gases all provide controlled environments where information flow across analog event horizons can be studied without the extreme conditions present near astrophysical black holes. These analog systems confirm that information can indeed be preserved in situations analogous to black hole formation and evaporation, supporting quantum mechanical expectations over classical general relativistic predictions. But the analogues necessarily simplify the full complexity of gravitational collapse, leaving open questions about whether their results apply to realistic black hole scenarios. The information continues its inward journey, carried by matter and radiation that cross event horizons in patterns too complex for classical observation to follow. Whether this information vanishes completely, becomes encoded in holographic patterns on horizon surfaces, or escapes through quantum mechanical processes that transcend classical spacetime geometry, it represents a frontier where our understanding of physical law encounters its deepest limitations. The black hole keeps its secrets at the boundary between quantum mechanics and general relativity, holding information in configurations that consciousness cannot yet decipher. The universe counts, not in the familiar arithmetic of whole numbers and fractions, but through discrete, indivisible units of space-time itself that might form the fundamental substrate from which continuous geometry emerges. Causal set theory proposes that the smooth manifolds of Einstein's general relativity represent approximations valid only at scales much larger than the basic granular structure of space and time. In this framework, space-time consists of discrete events connected by causal relationships rather than points embedded in a continuous manifold. Each event either influences another through light speed or slower connections, or remains causally disconnected from it. The network of these causal relationships forms a partially ordered set, a causal set, that encodes all the geometric and topological information usually described through metric tensors and curvature calculations. The fundamental postulate of causal set theory assumes that space-time contains a finite number of events in any bounded region, with the density of events determining the local curvature properties that general relativity describes through continuous field equations. Regions with higher event densities correspond to more strongly curved space-time, while regions with lower densities represent flatter geometric configurations. This discreteness resolves several conceptual problems that plague continuous approaches to quantum gravity. If space-time itself consists of discrete elements, then the infinite quantities that arise in quantum field theory calculations become automatically regulated at the Planck scale, where the discrete structure becomes apparent. The theory provides natural cutoffs for divergent integrals without requiring ad hoc renormalization procedures. The causal structure encoded in discrete event networks also preserves the causal relationships that general relativity demands while avoiding the paradoxes that arise when quantum mechanics meets continuous space-time. Information propagation follows the discrete causal links between events, eliminating the possibility of faster-than-light signaling or closed time-like curves that might violate causality principles. But translating familiar concepts from continuous general relativity into discrete causal set language requires careful attention to how geometric notions emerge from purely combinatorial data. The concept of distance must be derived from counting causal connections between events rather than measured using metric tensors. Curvature emerges from statistical properties of random walks through the causal network rather than differential geometric calculations involving Christoffel symbols and Riemann tensors. The Einstein field equations themselves must be reimagined as relationships between event densities and causal connectivity patterns, rather than partial differential equations relating metric components to stress energy tensors. This translation process remains incomplete, with no fully satisfactory discrete analogue of Einstein's field equations yet developed. Causal set theory makes specific predictions about the fundamental scale at which space-time discreteness should become apparent. The Planck length, roughly 10 circumflex 35 meters, represents the natural scale where quantum gravitational effects become important, suggesting that space-time granularity operates at this incredibly tiny distance. At scales much larger than the Planck length, the discrete structure should be invisible, with continuous geometry emerging as an accurate approximation. This emergence of continuous space-time from discrete foundations resembles how solid materials appear smooth and continuous at large scales, despite consisting of discrete atoms at microscopic scales. The granular structure becomes apparent only when probed with instruments sensitive to individual atomic spacing, while macroscopic observations reveal smooth, continuous properties like density and elasticity. Testing causal set theory's predictions requires detecting signatures of space-time discreteness in observable phenomena. The theory predicts specific correlations between cosmic acceleration and the discrete structure of space-time, suggesting that dark energy might arise from the fundamental granularity of space and time rather than from exotic matter fields or vacuum energy contributions. If the universe contains roughly 10 circumflex 183 causal set events within the observable horizon, as causal set theory estimates, then the discrete structure should produce fluctuations in cosmic expansion rates that might be detectable through precise measurements of distant supernova brightnesses or cosmic microwave background radiation patterns. These fluctuations would represent direct signatures of spacetime quantization, rather than indirect effects mediated through quantum field interactions. The theory also predicts that spacetime should exhibit preferred directions and discrete symmetries that break the continuous rotational and translational invariances of classical general relativity. These violations should be extremely small at observable scales, but might accumulate over cosmic distances and times in ways that produce detectable effects in high-precision astronomical observations. Gamma-ray bursts from distant galaxies provide particularly sensitive probes of spacetime discreteness, because their high-energy photons travel enormous distances through potentially granular spacetime. If spacetime possesses discrete structure, high-energy photons might experience slightly different propagation effects compared to lower-energy ones, producing energy-dependent arrival time delays that could reveal the fundamental scale of spacetime granularity. Current observations place stringent limits on spacetime discreteness that approach but do not yet reach the Planck scale. Sensitivity required to test causal set theory directly. Future space-based gamma-ray telescopes with improved timing resolution might detect the tiny temporal variations that discrete spacetime structure would produce in high-energy photon propagation. The combinatorial approach to quantum gravity also connects to other discrete approaches like loop quantum gravity and spin foam models, which similarly propose that continuous spacetime emerges from more fundamental discrete structures. These connections suggest that discreteness might represent a universal feature of quantum gravitational physics, rather than a peculiarity of specific theoretical approaches. But causal set theory faces significant challenges in reproducing the detailed predictions of general relativity in regimes where the continuous theory has been extensively tested. The emergence of smooth geometry from discrete causal structures requires careful analysis of how large-scale averages of discrete quantities reproduce the differential geometric relationships that govern planetary orbits, gravitational wave propagation, and other well-understood phenomena. The dimensional reduction problem presents particular difficulties. Causal sets naturally describe four-dimensional spacetime through their intrinsic causal structure. But the theory must explain why three spatial dimensions emerge at large scales rather than some other dimensionality. The mechanism that selects specific dimensional structures from the vast space of possible causal set configurations remains poorly understood. Modern research in causal set theory focuses on developing computational tools for analyzing large causal sets and extracting their emergent geometric properties. Monte Carlo simulations of random causal sets attempt to identify statistical signatures that might distinguish different geometric backgrounds and reveal how curvature and topology emerge from discrete foundations. The events continue their discrete existence in the fundamental causal network, each connected to others through relationships that respect causality while avoiding the infinities that plague continuous quantum field theories. Whether this granular substrate underlies the smooth spacetime that consciousness experiences, or represents another mathematical abstraction that fails to capture gravity's true nature. It persists as a reminder that familiar concepts like continuity and differentiability might be approximations that break down when reality reveals its most fundamental structure. The question remains, after decades of theoretical development, experimental innovation, and observational discovery, gravity's fundamental nature continues to elude complete understanding, whether force or geometry, emergence or illusion. The phenomenon that holds planets in orbit while consciousness puzzles over its mechanisms maintains its mysteries at the deepest levels of physical inquiry. Einstein's geometric revolution transformed gravity from Newton's mysterious action at a distance into the curvature of space-time itself. Yet this geometrization merely pushed the mystery deeper rather than resolving it completely. Why should matter tell space-time how to curve? What determines the specific mathematical relationship encoded in the field equations? How does curved geometry translate into the experienced phenomena of weight, tides, and orbital motion? The quantum mechanical description of matter and energy resists integration with geometric theories of gravity, creating conceptual gaps that hint at fundamental limitations in current theoretical frameworks. Perhaps both quantum mechanics and general relativity represent effective theories, accurate within their domains, but ultimately reducible to more basic principles that remain undiscovered. The holographic principle suggests that three-dimensional space might be illusory, projected from information encoded on two-dimensional surfaces in ways that create the appearance of depth and volume. If space-time itself emerges from quantum information, rather than providing the fundamental arena for physical processes, then gravity becomes a secondary phenomenon arising from more basic informational dynamics. Emergent gravity scenarios propose that gravitational attraction results from entropic forces created when matter and energy disturb the quantum entanglement patterns from which space-time arises. In this picture, massive objects do not curve pre-existing geometry but instead affect the information storage processes that give rise to geometric relationships. Space and time become derived concepts rather than fundamental aspects of reality. String theory attempts to unify gravity with quantum mechanics by treating all fundamental particles as vibrating loops moving through higher dimensional spaces. The extra dimensions remain hidden at scales too small for direct observation, but their existence provides natural explanations for gravity's relative weakness and creates possibilities for gravitational effects to deviate from Einstein's predictions under extreme conditions. Yet string theory's landscape of possible vacuum states contains so many alternatives that the theory loses predictive power, explaining everything while predicting nothing specific about the particular universe that consciousness inhabits. The mathematical elegance that initially attracted physicists to string approaches becomes a liability when translated into empirical consequences that remain beyond experimental reach. Modified gravity theories like MOND achieve remarkable success in explaining galactic dynamics without invoking invisible dark matter, suggesting that gravitational physics itself requires revision at cosmic scales. But these modifications struggle to maintain consistency with general relativity's well-tested predictions while extending smoothly to cosmological contexts where structure formation and cosmic acceleration must be explained. The dark matter paradigm preserves general relativity's mathematical structure while invoking new particles that interact gravitationally but remain invisible to electromagnetic detection. Decades of increasingly sophisticated experiments have failed to detect these particles directly, raising questions about whether dark matter represents a fundamental component of nature or a theoretical placeholder for incomplete understanding of gravitational physics. Dark energy drives cosmic acceleration through mechanisms that connect to quantum field theory's predictions about vacuum energy in ways that create the worst theoretical prediction in the history of physics. The enormous discrepancy between calculated and observed vacuum energy densities suggests fundamental misunderstandings about how quantum mechanics and general relativity relate to each other. Black holes concentrate these mysteries into regions where quantum mechanics and gravity meet under the most extreme conditions accessible to theoretical analysis. The information paradox reveals contradictions between quantum mechanical unitarity and general relativistic event horizons that persist despite decades of sophisticated theoretical attempts at resolution. Causal set theory and other discrete approaches to quantum gravity propose that spacetime itself consists of fundamental granular units that create the illusion of continuity at large scales. These discrete structures avoid the infinities that plague continuous field theories, while creating new challenges in explaining how familiar geometric concepts emerge from purely combinatorial foundations. The experimental frontier continues advancing through gravitational wave astronomy, precision tests of the equivalence principle, searches for extra dimensions, and attempts to detect quantum gravitational effects in laboratory settings. Each new observation constrains theoretical possibilities while revealing phenomena that existing frameworks struggle to accommodate completely. Yet perhaps the deepest mystery lies not in the technical details of field equations or particle interactions, but in the relationship between mathematical description and physical reality itself. Why should the universe be comprehensible to consciousness through mathematical relationships? What determines which mathematical structures correspond to actual physical phenomena rather than mere formal possibilities? The anthropic principle suggests that physical constants and laws might be selected through observer effects in infinite ensembles of possible universes, replacing dynamical explanations with statistical arguments about the conditions necessary for conscious observation. But this approach raises uncomfortable questions about the relationship between physical law and awareness, making consciousness a fundamental ingredient in cosmic evolution rather than an emergent byproduct of complex matter arrangements. If gravity emerges from quantum information, quantum entanglement, or other microscopic processes that remain hidden from direct observation, then the familiar experience of weight and falling might represent just one layer in an infinite hierarchy of emergent phenomena. Each level appears fundamental when viewed from appropriate scales, but reveals its derivative character when examined from perspectives that encompass larger or smaller domains. The question echoes through conference halls and research papers, driving theoretical development and experimental innovation without reaching definitive resolution. Gravity continues its patient work throughout the cosmos, holding planetary systems together while galaxies drift apart in the expanding universe. Maintaining patterns of cosmic structure that consciousness attempts to understand through mathematical abstractions and empirical observations, whether the answer lies in quantum information, extra dimensions, discrete space-time, modified field equations, or conceptual frameworks not yet imagined, gravity maintains its status as both the most familiar and most mysterious of physical phenomena. The apple still falls from Newton's tree, following geodesic paths through curved space-time while consciousness wonders whether space-time itself might be the universe's most sophisticated illusion, masking deeper truths about the nature of existence that remain suspended between theoretical possibility and empirical confirmation. The cosmic dance slows. Galaxies drift apart in the expanding universe, their spiral arms uncoiling over billions of years as dark energy drives accelerated expansion toward futures where isolated stellar remnants will shine alone in infinite darkness. The grand structures that gravity assembled during cosmic youth gradually surrender to entropy's patient dissolution. Yet, in this cosmic twilight, the questions persist with quiet intensity. Gravity maintains its ancient mysteries even as it guides the universe toward maximum entropy states where no further evolution remains possible. Whether force or illusion, emergence or fundamental geometry, the phenomenon that shapes cosmic architecture continues its work while consciousness struggles to penetrate its deepest secrets. The mathematical frameworks multiply and compete, each capturing partial truths about gravitational phenomena without achieving complete understanding. String theory's extra dimensions curl beyond observational reach. Quantum information patterns entangle across cosmic distances. Discrete spacetime structures count events at scales too small for direct detection. Modified gravity equations explain galactic dynamics through mechanisms that resist cosmological extension. Perhaps the mystery itself represents gravity's most fundamental characteristic, not a temporary limitation of current knowledge, but an intrinsic feature of how consciousness encounters physical reality. The questions that drive scientific inquiry might be more fundamental than the answers they seek, creating the investigative processes through which awareness explores its own cosmic context. The universe settles into patterns of increasing entropy, stellar formation rates declining as gas supplies become exhausted and galactic collisions scatter stars into eccentric orbits around supermassive black holes. Eventually, even these black holes will evaporate through Hawking radiation, leaving only elementary particles drifting through exponentially expanding space at temperatures approaching absolute zero. In those far futures, if consciousness persists in forms we cannot imagine, perhaps the nature of gravity will finally become clear, or perhaps the mystery will deepen, revealing new layers of illusion beneath the geometric structures that currently seem fundamental. The question remains suspended in cosmic time, patient as gravity itself, waiting for understanding that may require eons of continued investigation. Sleep well, gentle travelers, in the gravitational embrace that holds all existence together while keeping its deepest secrets hidden in mathematical abstractions too beautiful for complete comprehension.